Hi, welcome to Physics Teacher, the channel that prepares you for the Waterloo Math and Science Contest. This is a grade 11 Math Hypatia contest question. It's question 3 from the year 2021, and in it we have 2 sequences and 3 questions regarding those sequences. The last one being that you need to determine the smallest number of terms in sequence B so that the sum of all those terms is greater than or equal to 16 to the power of 2021. Give them a try, and I'll be right back with all their solutions. Alright, so let's start with part A. Part A is simply asking for the 5th term in both of these sequences. So let's see what these sequences are. The first sequence, sequence A, is 2 to the power of n. So the first term would be 2 to the power of 1. The second term, 2 to the power of 2, and so on until we get to the 5th term, which is going to be A5, will be 2 to the power of 5, which is 32. Alright, so let's look at the second sequence. The second sequence starts with 1. And then the second term is also 1. And then the third term, we need to use this expression to calculate it. So this pretty much says that this is the previous term, which would be 1, plus twice the term before that, which is 1. So plus 2 times 1. So the third term, B3, is going to be equal to 3. Alright, well what about B4? Well, B4 is equal to B3 plus 2 times of B1, where B3 is 3 and B2 is 1. So B4 will have a value of 5. Finally, our 5th term is going to be our 4th term plus twice our 3rd term. So our 4th term is 5. And twice our 3rd term is twice times 3. So that's 6 plus 5 gives us 11. So the 5th term in sequence B is 11. Alright, let's move on to part B. Now part B, we have this expression here, and we need to solve for the real numbers P and Q. Well, let's start with B1. B1, we know has a value of 1, and it is equal to P times A1 plus Q times negative 1 to the power of 1. Alright, A1, if you go look at A1 would simply be 2 to the power of 1. So we know A1 is 2. So now we have 1 equals 2, P times 2, or just 2P, plus Q, and negative 1 to the power of 1 is just negative 1. So this tells us that 1 is equal to 2p minus q. Let's call this equation 1. Now let's go look what B2 is. B2 has also a value of 1, and it is equal to p times A2 plus q times negative 1 squared. Alright, so here we have 1. A2 is simply 2 to the power of 2, which is 4. So that's going to give us 4p. And negative 1 squared is positive 1, so plus q. So now we have 1 equal to 4p plus q. Let's call that equation 2. So now we have 2 equations with 2 unknowns. I'm going to rewrite the second equation down here so that you can see a great way of solving them is to simply add those equations together. Because our q's will cancel, and it will simply give us 2 is equal to 6p. If 2 is equal to 6p, then we know p is equal to 1/3. Now that we know p is equal to 1/3, let's take equation 1 again. And we have 1 equals 2 times the third minus q. Or rearranging, we get q equals 2/3 minus 1, which gives us a value of q as negative 1/3. So there's our answer for part B. All right, moving on to the final part, part C. Part C says let Sn be the sum of the first n terms in sequence B. Determine the smallest positive integer n that satisfies this. All right, so Sn, that's the sum of all the terms in B. So what we would have is B1 plus B2 plus B3 all the way up to whatever the value of n actually is, plus Bn. All right, so let's substitute what Bn actually is, because from part B we have an expression for that, and we've also solved for P and Q as well. So let me rewrite the values of P. So we have P as 1/3 and Q as -1/3. So that means we can write B1 here as P, which is 1/3, and I'm going to put brackets in here, all times by A1 minus 1/3, because Q is -1/3, times -1 to the power of n, which is for the first term 1. All right, well, now let's add B2. So B2 is going to be 1/3 times A2 minus 1/3 times -1 squared. And we can keep doing that all the way up to Bn, which would be 1/3 An minus 1/3, I'm going to run out of room, minus 1/3 times -1 to the n. All right. So let's simplify this a little bit, because what we can see is here we have 1/3 A1 plus 1/3 A2 plus 1/3 A3, 1/3 A4, all the way up to plus 1/3 A1. So let me factor out that 1/3, where we then have A1 plus A2 all the way up to An. Then we have this common factor, minus 1/3. And then we have -1, and this is squared, so it's going to be plus 1, and then cubed would be -1 plus 1, -1 plus 1. So we have 1/3 all times by -1 plus 1, -1 plus 1, all the way up to -1 to the power of n. All right, let's continue this a little bit further, because we know what A1 is. A1 is 2 to the power of 1. A2 is 2 to the power of 2. A3 is 2 to the power of 3, and so on all the way up to An, which is 2 to the power of n. And then we still have this minus 1/3 of -1 plus 1 minus 1, all the way up until -1 to the power of n. All right, so let's look at this first bracket here. Now this is a geometric sequence with first term, or A, as 2, and a common ratio R as 2, because it goes up each time by a factor of 2. Now on the exam, it does give you an equation for the sum of a geometric sequence, and that equation is that first term A, all times by 1 minus that common ratio R to the power of n, divided by 1 minus R. And that is as long as R does not equal 1, because then you'd be dividing by 0. So in our case, this first bracket has a sum of 2 times 1 minus 2 to the n, all over 1 minus 2. Now 1 minus 2 is just -1, so this simplifies to -2 times 1 minus 2 to the power of n. All right, let's look at the second bracket here. This second bracket can either start at -1, so you're going to have a value of -1 if the value of n is odd, but if it's even, you're going to add 1, giving you 0 if n is even. So we have two possible scenarios for our second bracket. So simplifying, the sum Sn for our second sequence, you can write this as a piecewise function. It's either going to be 1/3 times by negative 2 times 1 minus 2 to the n. And if this is going to be even, so if n is even, then that whole second term here becomes 0. Now, if n is odd, our sum is going to be 1/3 times negative 2 times 1 minus 2 to the power of n. And then if n is odd, this whole term will be negative 1. Multiplying by negative 1/3 gives us positive 1/3. Now, let's go back to that restriction we need to satisfy, where this sum is greater than or equal to 16 to the power of 2021. So we can sort of change that a little bit, since we do have powers of 2's in here. We'll say this is greater than or equal to, instead of 16, I'll replace 16 with 2 to the power of 4, and that's all to the power of 2021. So that means the sum must be greater than or equal to 2 to the power of 8,084. All right, let's look at our two cases. So if n is even, or if n is odd. So if n is even, here we have 1/3 times negative 2. So we have negative 2/3 times 1 minus 2 to the power of n must be greater than or equal to 2 to the power of 8,084. Or let's bring that negative into the bracket, which would give us 2/3 times 2 to the n minus 1 is greater than or equal to 2 to the power of 8,084. If we multiply by 3 and divide by 2, we have 2n minus 1 is greater than, so multiplying by 3, times by, if we divide by 2, we simply subtract 1 from the exponents. So we have 2 to the power of 8,083. And then what we can do is just simply add 1 to both sides. All right, well, what about if it's odd? Well, if it's odd, we can simplify this in the same way. So let's multiply by 1/3, and we'll throw the negative into the brackets. That gives us 2/3 times 2 to the power of n minus 1. And then we have this plus 1/3 on the end. And that must be greater than or equal to 2 to the power of 8,084. So we're going to have to subtract 1/3 from both sides. So that's going to give us 2/3 is 2 to the n minus 1 is greater than 2 to the 8084 minus 1/3. Multiply by 3 and divide by 2. We have 2n minus 1 is greater than or equal to 3 times 2 to the power of 8083. And similarly with this fraction here, we have to multiply by 3 and divide by 2, which gives us minus 1/2. If we add the 1, we have 2 to the power of n is greater than or equal to 3 times 2 to the power of 8083 plus 1/2. All right, so let me rewrite these results, and then we're going to analyze them. First thing that we can notice is 2 to the power of n is an even integer in itself, as well as this expression here is going to be an odd integer. Whereas this expression, since we're adding a half, is going to be somewhere in between an odd and an even integer. So it's neither odd nor even. Another thing to notice is that 3 times 2 to the 883 is going to be greater than if we were to simply have 2 times 2 to the 883. I think that's obvious there. And 2 times 2 to the 883 is the same as 2 to the 8084. So if we want the smallest possible integer n that satisfies this sum, then this must be also less than or equal to 2 to the n. Now if you were to have 2 to the power of 8085, well, that's the same as 2 times 2 to the power of 8084, or 2 squared times 2 to the power of 83. And 2 squared is 4 times 2 to the 83. And that is clearly greater than this. Therefore, n must be equal to 8,085.